Hello and welcome. In this video, we're going to talk about some tips how to solve a couple of homework problems that represent typical homework problems from an introductory astronomy class. Specifically, two homework problems about the sun. Okay, so both of these problems involve our sun, our local star, as the topic. The first one is all about, as it says, humans' ability to collect power. So this one we'll call the intensity. All right, and power of the sun. And we can see a few parts of it, A, B, C, and D. I follow through on some interesting ideas, so I hope you will enjoy the question. And then in the second one, which we'll get to in a minute, but I would like the title right now, this one's all about fusion, all right? So this is going to be fusion supply and energy. So I'll call this fusion supply and energy output. Okay, so those are our working titles for our two problems that we're going to be taking a look at. All right, so let's read number one. We will consider humanity's ability to collect power from the sun in this problem. The sun has a luminosity of, let's go ahead and highlight this, 3.84 times 10 to the 26 watts. It also has the diameter. We're going to need its radius, but let's record this as well. Okay, using the inverse square law, which is a relationship between luminosity and distance from the center of the source of that luminosity, we can find out the intensity of sunlight that reaches Earth at a distance of 149 million kilometers, which is 1 astronomical unit. And we're going to give this in the base units of intensity, which is watts per square meter, because intensity is power per area, or since power is energy per area, then what we have is, energy per time. That's what power is. That means that intensity is energy per time per area, okay? Because that's exactly what watts per area tells us. So let's take a look and get the key ideas thinking about how we would solve this. Okay, so I won't be solving the problem here, but I'm going to give you some tips on how to solve it. So looking at part A, what is our unknown? What are we trying to solve for? We're trying to solve for R, which is going to be, or rather, we're trying to solve for L because we know everything else. So our one unknown is L, okay? Where L is the intensity of light at Earth. Intensity of light at Earth, okay? Do we know the intensity of the light at the surface of the sun? Yes, we certainly do. This right here, L, is, for the sake of the formula, L naught. Okay, not trying to give it two different names. It's just because, relative to any other value of intensity, it is the original, the baseline intensity. So it makes sense to refer to it as L naught. But if we're referring to the luminosity of the sun, we don't necessarily have that subscript. Okay, so we're trying to solve for L, which would be our variable here. And we also know these distances. Okay, how is that? Well, importantly, we know the baseline radius, because you can't actually put a value of 0 in here. You can't have a luminosity of something that has no defined radius. So we have to consider that this is the total surface area of which this whole energy is coming out of, because conservation of energy is a pretty strict rule. We always have to be able to track where it comes from, in this case, from the surface of the sun. But we can certainly come up with that. And by the way, this relationship here between square radiuses is really actually a ratio of the area that this energy is fluxing through. So there's an energy flux through a certain enclosed area that itself encloses a volume. But my point is that it's a sphere, because the energy is spreading out from the sun, and it's spreading out, and you can enclose it in a sphere at any particular radius, any particular distance from the sun. This is a source of energy, right? Well, the thing is that the aspects of the sphere, the formula, which is namely 4 pi r squared, the surface area of a sphere formula, well, the 4 pi cancels out because we have a 4 pi in both cases. That's why we're just looking at a ratio of radii. Already kind of did that upfront cancellation. So then what you're going to, when you think about this, you're simply going to put in the right units and solve for the luminosity of Earth based off the baseline luminosity and the 2 radii. All right, so the baseline radii, which is the smaller value squared, and then the actual radius, or in this case, you can think of it as the distance from the center of the sun to the Earth, which is Earth's distance of 149 million kilometers. Now, pretty nice. Both the values are actually millions of kilometers, so you can certainly get away with keeping them in that units because you're going to be taking that ratio and looking at them. I'm trying to think though, yeah, because if you factored out the 10 to the 6 in both cases and dealt with it being squared in both cases, which I forgot one of them, then that order of magnitude would cancel out even with the square. Okay, so enough about part A. In part B of this problem, we're asked now to consider that the average total energy consumption of the United States is this particular value. Okay, big number as you would expect. All right, so 10 to the 21 joules. So what is the average power requirement for the United States in watts? Okay, so this one should just be a straightforward calculation. It's really kind of a step to things to come. And actually, I'm going to put this over here. All right, so for part B, what you really need to care about is just the formula for how to get energy to watts. So that's what I'm looking for here. So this is really a definition, and we can say that watts, all right, as a unit are joules per time. So these are all names of units, although this would be a second, if I'm being consistent with calling them units. If I was to call them variables, it would be power, energy, and time. So it look like this, power equals energy per time. You can always think about it in either of those ways, whether you're thinking about the units and that's what you're paying attention to, or you're thinking about the names of the quantities. They are often interchangeable in terms of how you actually want to approach a problem. Point being, in this case, you're being asked for watts for the power, and since you know the energy, do you also know the time? Well, you do, because it says annual. So right there, that is your other number, all right? Sometimes these values can be kind of hidden, not given up front. And since joules are based in, well, base units, which involve seconds, we got to make sure that we're going to be putting our time into seconds as well. So you will need to put the time into seconds, which will involve converting the 1 year, because that is your period, to seconds. Because only then can you enter that value for time and your energy is ready to go. Okay, so take that ratio, and that's going to be your wattage, which is your power output, or in this case, your power consumption, what the United States and all the people in it require for power. Okay, so now why does that number matter? Well, for part C, you're going to think about how could you generate that power entirely from the sun. Okay, which is totally reasonable. In fact, you'll see there's more than enough energy coming from the sun. If solar cells can convert sunlight into electrical power at 30% efficiency, which is a little bit better than most numbers you currently find if you look for average efficiency for solar conversion, even at the industrial scale. But we're going to take 30%. We're being very generous. Okay. Then how much total land area would need to be covered in solar cells to entirely meet the United States power requirements? Give your answer in square kilometers. Okay. So how the heck would we go about doing something like this? Well, remember, we solved for luminosity, right? So the luminosity we solved for in A, so we'll say from A, okay. Well, that value, if we consider its units, we can really make sense of what we need to do with it, because it has units of watts per square meter. Well, watts is exactly what we solved for in part B. That's what we need to have. If we're going to meet the needs of the nation, we need to be producing enough power per year. So we simply need to match the watts of the solar array to the watts of demand, all right, that you solve for in part B. Okay, and why did I mention the luminosity from A? Well, that's going to show up directly in the expression on the left-hand side of this equation, the watts of the solar array. Because what does the solar array do? Well, it takes the luminosity, all right, the value that you solve for from part A, which, big hint, should be something a little bit more than 1,000. So in the range of 1 to 2,000, okay, closer to 1,000. So once you solve for that value, luminosity at Earth, let's even put a little e there. No reason not to, all right? I didn't end the body of the problem, but I think it's a good subscript. So the luminosity of the sun as measured at Earth, right? Every planet has different values. Further you get, they fall off, right, with the square of the distance. So then, again, that is power per area. So if we multiply it by area, then we get power, right? So that is our unknown. This is the area of the array. All right, so your unknown is that value right there, the area of the array. As if you were to stick with the units as given, then you're going to have a case where the units will be in, well, so you got square kilometers, right? So oh, that's in the future. Okay, so let's see. Now, in this case, it's going to give it to you in square meters. Okay, because right now your luminosity is going to be in base units. Everything else is going to be in base units as well, including the wattage that you saw from B. Because as I write this equal sign, this value right here, wattage, of US demand is exactly your answer from part B. All right, so you're taking answers from A and B. All right, so let's make a point, as I mentioned. All right, this is just from B. Okay, so then solve for the area of the array. That will be in meters, okay, square meters. I do ask you to convert it to square kilometers, so don't forget that last step. Convert, because as the formula is written, it's going to be in square meters. So convert to square kilometers. Okay, all right, so that's it for part C. The last part considers this hypothetical future case where we're going to be able to put a big giant array that is 50,000 square kilometers, which is, by the way, is going to be a bigger value than you got. You're going to get a pretty big number for part C. It takes a lot of land area, but maybe not as much as you expect, totally doable. And it's just the infrastructure and everything to make it happen. But in this case, we have a number that's going to be a little bigger, right? Not that much bigger, but definitely bigger, 50,000 square kilometers, giant array, but we're going to put it into space. And very importantly, we're going to put it really close to the sun, actually interior of Mercury's orbit. So that's going to create a big increase in luminosity. So for this last part, you're going to find a new luminosity, we'll just call it llama or L prime, and you're going to find this one by taking the baseline, just like we found the luminosity to Earth. But in this case, you compare the radius of the sun to this new radius, which is just going to be the 10 million kilometers, right? A much smaller value than 150 million kilometers, right? And since it's a squared relationship, this doesn't have a big effect. And since your luminosity has gone way up, when you actually calculate the wattage, well, I won't give this away, but it's the formula we were just talking about. So you can certainly use this formula to calculate the wattage, because in this case, you're given A, all right? And I haven't mentioned efficiency, and I don't want to leave that out, because currently you would think you don't even need to consider it. It shows up right here where you actually get the how much you get from it. Because if you think about it, this is the output and this is the demand. Well, the output is limited, so essentially has you multiplied by efficiency. So we'll put it right in front. So E for efficiency would show up right there. Here, since it was kind of just general, the power output. So once you go from how much wattage the solar array can produce and actually include the quantities of luminosity and square area, well, that's where you have to put in the efficiency, because that's going to drop you to something better than the best case, because otherwise it would just be LA, because that would be an efficiency of, well, 1, which is 100%. So in this case, if we had an efficiency of, well, 30%, you don't put 30%, you need to put as a fraction. So it's just E equals 0.3. Likewise for D, with this futuristic, even higher efficiency, the first one already being pretty generous, in this case, it's going to be 0.6. All right, so that'll show up right in front. All right, and then all the steps are the same, and you'll be able to calculate the not area this time, but rather how much wattage you get, right? Because there's no particular demand we're trying to meet, but should be a lot of power, all right? Should be more than enough for the current United States. But by that point, this would be pretty far in the future, so I imagine there would be more power demands to meet. So we're chasing a moving target in that respect. It's like the Queen in Alice in Wonderland. We just keep running and running and running and running. All right, the red queen theory, or the red queen idea, applied to a biology, but here applied in a very different way to the idea of luminosity. Okay, and well, getting energy from it, collecting energy. So how does the sun collect energy? The sun isn't just using solar panels to collect energy. The sun is the source of that energy that we're trying to capture some small amount of, because the sun creates energy in a very unique way. It creates it with nuclear fusion. Now, here on Earth, we have nuclear fission. This leads to nuclear bombs. We actually also have nuclear bombs that are fusion bombs. But in terms of power production, less harmful means of nuclear processes, all of the power plants that involve nuclear energy are all fission. They involve the breaking up of large nuclei, like uranium. But here we're talking about fusion, which is the fusing of small nuclei. which is actually a better energy return in terms of the process. And also it has, if we were to do it on Earth, wouldn't have the same kind of harmful side effects. Okay, still a very high energy affair though. Okay, so what goes on in this problem? Well, let's take a look at part A. All right, well, we'll start reading it. The sun's chemical composition was about 70% hydrogen when it formed, and about 13% of this hydrogen was available for eventual fusion in the core. The rest remains in layers in the sun where the temperature is currently too low for fusion. A lot of it will always remain there, and then has an eventual fate, much of it being pushed out into a planetary nebula at some point. But point being is that a lot of it never has a chance to get fused. Maybe it will in the next generation of sun or star, that'll get picked up in and then kind of gravitationally contract into. But regardless, this composition is kind of indicative of the universe as a whole. The universe is mostly hydrogen and helium. Okay. So the mass of the sun here is given as 1.99 times 10 to the 30 kilograms, pretty accurate number as far as we know. Use the given data to calculate the total mass of hydrogen available for fusion over the lifetime of the sun. And we're going to give this in kilograms, okay? So we need, just based on the percentage we were given, what is our available, fuel, all right? So M available in this case is just a series of ratios, okay? It's just going to be your relevant ratios to get there, right? So M available is found, I don't want to give it away exactly, right? By considering the two ratios, because you're going to take 70% of the total mass and then take 13% of that, okay? It still will be a very large mass, but it's not going to be most of the sun, okay? So that's going to be it for part A. As far as B is concerned, in this case, we get into some other values. We're now told the sun fuses about 600 billion kilograms of hydrogen each second. And we're already working in kilograms, so our value here will already be in kg, because again, you're just multiplying by a couple of percentages, okay? But again, change them to decimals. I say again because I mentioned in the last problem that is. So your 70%, you need to turn that to a 0.7. Likewise, it needs to be turn into a 0.13. Remember, you do one, then the other, as it's described, okay, in terms of taking those ratios. You get a final answer in kilograms, all right? Well, point being is that now we have a certain rate of using that mass up, that available fuel, and we're using it 600 billion kilograms every second. So what we have here is a rate, okay, of fuel use, okay? Fuel use is the same as available mass. Available mass is fuel. Fuel is available mass. So rate of fuel use is going to be that 600 billion, so 600 times 10 to the 9 kilograms per second, all right? So from that, you should then be able to calculate how long the sun's initial supply of hydrogen can last. Your answer will be in seconds from the calculation is given, pretty straightforward, but then you need to convert it to years, as is mentioned up here. I know it said it. So initial will last, yes, in years, okay? So we just use our value of 600. That was our new number that we introduced, and we ended up with a time, okay? So then convert to years, all right? Convert. The last time it was already in kilograms, so it said in kg here, so it should say convert to years, all right? So in part C, what are we doing? Now we're told that given that our solar system is now about 4.6 billion years old, when will we need to worry about the sun running out of hydrogen for fuel? Well, you have a lifespan based on our rate and our available mass, right? Because indeed, that is what you solved for, okay? In part B, that was the lifespan. So then what you should be able to figure out is if you have the lifespan and we have the total age, how do we find out how much age is left? Okay, so they're simply going to relate the total lifespan to current age, right, and remaining time. And what's being asked for is, of course, the remaining time. All right, so the last part of the problem, I believe, is, last part is part D. So in part D, we're going to put in a little bit more actual energy calculations and just more calculations in general. Consider the sun's total supply of hydrogen available for fusion that you found in A. Okay, so you directly use your value in A, in kilograms. Then you're going to say that 0.7% of that mass is converted to energy. Notice this is not 0.7 like as a ratio. This isn't saying 70% and then already converted it to a decimal. This is 0.7%. So once you turn this to a ratio, it'll be 0.007, Okay, so it's a small amount, in other words, because that's exactly how fusion works. Only a small amount of mass is actually converted to energy. Okay, but considering that, right, that's going to be how much total mass disappeared. Okay, because that amount of mass is completely changed to energy, either the kinetic energy of the particles that were produced through the process of fusion, or just pure light energy in the case of gamma rays. Okay, or some of it kind of indirectly in terms of the positrons that are produced that very quickly get annihilated with an electron, again producing a gamma ray. All that aside, what are you actually doing here? You're going to be calculating based on that change in mass, E. All right, so your unknown is E, so you're going to find E. All right, you're going to find that with the formula, E equals mc squared. C is just the speed of light, so it's just 3 times 10 to the 8 meters per second. Don't forget to square it. M is the only thing you have to put some work into, okay? M is going to be your not available mass, but 0.07% of available mass. So right, it's not 0.07, but 0.7%, don't forget to convert to a decimal, of available mass, where available mass is your answer that you got from part A, right, when it was in kilograms, all right? And this formula, Einstein's, formula, E equals mc squared, is ready with kilograms, so as long as you plug those in, the answer you get will be in joules, okay? And so that will be the total amount of energy, it says right there, that you are going to report. And in fact, I don't say it, I should have, but you're going to report it in joules. So report in joules, which will be the unit it is already in, because kilograms, meters per second. Okay, well, that's it for this video, giving you some homework tips for a couple of introductory astronomy problems about the sun. I hope this video has been helpful and informative. Thank you so much for watching.